All right, today we'll look at something called continuity, and then based on that we'll look at the intermediate value theorem. Let's talk about continuity. So if you want to pause the video and copy all these, do that now. Um, so which functions are continuous and why? There's a definition of continuity to point, and we're going to look at where that definition comes from. So looking at a graph, it's easy to say whether something is continuous. It's just, is it broken or not? And that's a closed circle there. So if you can trace it, but you have to lift the pen, then it's not continuous. So we know this is not continuous. And now we have to come up with a reason why is it not continuous. And I think we should say that f of a, this y value is f of a. And we can say that f of a is not approached from both sides. So if we look at that value, from the left, it is approached. From the right, some other y value is approached. And that's the problem with this function. Now let's look at this one. Can we trace it without lifting the pen? No, we have to lift it. There's a little missing point there. So we would say that it's not continuous. And the reason why would be f of a does not exist. If there was a value there, then it would be continuous. We're going along the function. We have to jump up there and jump back down. And so we would say it's not continuous. And the reason why would be f of a is not approached. So if we follow the graph from the right, we're not approaching f of a. There's f of a. This is approaching some other y value from both sides. All right, and we look at this graph, and we can trace it without lifting the pen. So that is continuous. And over here, we trace the graph, it goes up, but then we have to go back down and restart down there. So this is not continuous at A. And we could say that f of A does not exist. All right. So we have discontinuity when f of a is not approached. And we have that over there. F of a is not approached from both sides. We also have discontinuity when f of a does not exist. So f of a does not exist here. F of a does not exist there. So those are two causes for a discontinuity. When we have continuity, we could say that f of a exists and is approached from both sides. All right, and then let's throw in some vocabulary. When the graph jumps, it's called a jump discontinuity. When there's just a hole in the graph, it's usually a removable discontinuity. And this, it jumps up, so that's a jump discontinuity. And here this is called an infinite discontinuity. All right, and we talk about approaching a value. That's going to be a limit. The limit is the y value that a function approaches. So let's talk about limits. Find the value approached by So if we had this statement, or statement, find the value approached by the function as x approaches 2, we can write that like this. Find the limit of x squared as x goes to 2. And we know that the function is approaching the y value of 4. So that's how we can have all these words put into these symbols in this statement. So now that we have that notation for a limit, we'll talk about the definition of continuity at a point. So we need to have the y value has to be approached, and the y value has to exist. The y value exists, the y value is approached from both sides, and that means it will be continuous. All right, and usually it's just written like this. That's the definition, but I think there's a lot of meaning in this that students miss. So we have to just look at the function exists, the limit exists, and they're going to the same place. The function is going to this from both sides, is approaching its y value. All right, so how can we talk about limits? So this is not continuity, it's just looking at a limit. And we have x squared. We need to get close to 2, so that could be 2.01, 2.1, 1.99, 1.9. We want to look at what are the y values doing from both sides. So we can follow these y values, 4.4, 4.04, this looks like it's going to 4. 3.6, 3.96, that looks like it's going to 4. So here, these values are the limit. This is the function value when we're looking at the table. So we can say that the limit of x squared as x goes to 2 equals 4. And we see it right there. The limit is looking at what are the y values getting close to, and that's the actual function value. In this problem, they're all the same. All right, try the next one. Pause the video. So, hopefully you chose the right values that are getting close to -1. We have to go backwards because we're going on the negative side, so the numbers are getting bigger going this way. -2.33. And we just look at -1.7, -1.97. Looks like these are getting close to -2. -2.3, -2.03. Those are getting close to -2. So we see that the limit of x cubed minus 1 as x goes to -1 equals -2, because from both sides it's going to -2. Alright, now we'll talk about continuity, where we have to see that there is a y value and the limit is the same as that y value of the function. So let's look at a table. And we need to get close to 2. And we get 0.2439, 0.2494, undefined, 0.25063, 0.2564. All right. What are those numbers getting close to? 0.243, 0.249. Looks like they might be getting close to 0.25. 0.256, 0.2506, close to 0.25. But the function is undefined at 2. So let's check our definition of continuity. Number 1, does f of 2 exist? No, so it can't be continuous. Let's look at this. The next one, does the limit as x goes to 2 exist? Yes. But since the function doesn't exist, it is not continuous. If we look at, though, when we have this, the limit existing but the function doesn't exist, and there's just going to be a hole in the graph. At 2, there will be an open circle, and the graph will cover the graphing later, but that's what the graph looks like. We have an open circle there, so that we would say that this is a removable discontinuity. And it's also called removable because it can be removed. So if we just factor the denominator and we go like that, now it's no longer, this is no longer undefined at +2. It is undefined at -2. So that's That cancellation is why they call it a removable discontinuity. All right, pause the video and see if this is continuous at 4. So we're getting close to 4, and we will, these numbers are getting close to 4. Use a calculator, find these values. Undefined. So we look for the limit from the right. It looks like it's going to positive infinity. Here from the left, it looks like it's going to negative infinity, and that's undefined. So that looks like a vertical asymptote. If we go through our list, our test for continuity, f of 4 exists? No. The limit of f of x as x goes to 4 exists? No. So we know it's not continuous, and because of these infinities, we know it's an infinite discontinuity. All right, a new question. F of x continuous at x equals negative 3. Question mark. Is it continuous at negative 3? All right, we'll just make a table. If you're confident with this one, then pause the video and try it. Remember that when we look at a piecewise function, here we're dividing it up at negative 3, so we want to use 3x minus 2 on the left, 2 minus x on the right. 3 is in the center, negative 3. So we have to get close to negative 3. Negative 2.99, negative 2.9. Negative 3.01, negative 3.1. Then we just need to find all the y values and see what they're getting close to. So in the calculator we would get these. Also remember that these numbers go into this. 2 minus negative 2.9 gives us that. 2 minus this is that. 2 minus negative 3 is 5. But over here we need to use 3x minus 2. Put this in for x, and we'll get negative 11.03, negative 11.3. So the limit from the right is 5, but the limit from the left looks like it's negative 11. So now we go through the list. Does f of negative 3 exist? No. Yes. Does the limit of f as x goes to negative 3 exist? No. Here the limit doesn't exist because it's going to 2 different values. So when the limit doesn't exist, we'll say that there's a jump discontinuity. Okay, with continuity, we can talk about the intermediate value theorem. And let's start with a question. I think this sounds a lot more difficult than it is. All right, so we have a function, and we only know 2 points on the function, 3, 2, and 6, negative 1. And here's the question: must f of x have a y value of 0? And usually we don't say a y value of 0, we just say it has a 0. If this is true, then we say that it has a 0. So we only know 2 values. Between 3 and 6, does the graph have to cross the x-axis? And we'll say no, because what if the graph went like this and just skipped the y value of 0? That's possible. And this graph, this function, is not continuous. So for the intermediate value theorem, we're going to say that the function has to be continuous. So here's the intermediate value theorem. If f of x is continuous, on an interval, then there's a number between a and b such that the y value of that number is between the y values of a and b. And that can be a little confusing too, especially with this such that and this symbol. This just means there's an element of. If there is a number that's an element of the set from a to b such that the y value is between the other two y values. So it's pretty a simple concept with some new vocabulary. Let's just see what that looks like. Here's an interval from a to b, and we know that f of a is there. We know that f of b is there. And we also know that if f is continuous, then there must be some c, then there is a c, such that its y value will be between the y value of a and the y value of b. And most a common use of the intermediate value theorem is just to look for a 0. So here's an x-intercept or a 0. If you start above the x-axis and you end below, then you have to cross. And that's all it's saying. That's all we're going to use it for. All right. So somewhere on this interval, this function has x-intercepts, also called zeros. So if we just find all the y values of these x values, we can find out where there must be an x-intercept. And with a calculator, we'll find the y values, and then we can identify where the x-intercepts are, or the zeros. Using the intermediate value theorem, even right here, we don't have to look for a zero. We know that between the x values of -4 and -3, there must be a y value of 20. So they're just saying that there will be a y value for each y value between here. If we're specifically looking for a zero, then we need to look for a sign change. So here at -3, it's above the x-axis, and then it's below the x-axis. Well, if it goes from above to below, it must cross the x-axis because it's continuous. Polynomials are continuous. So we know that y equals 0 on the interval -3 to -2. Then we're looking down here, it goes from negative to positive. So y equals 0 somewhere between here. On the interval -1 to 0, there is a y value of 0. And here from positive to negative, we have a y value of 0 on the interval 2 to 3. And that's all we're doing with the intermediate value theorem. So pause the video and try the next one. All right, and we looks like well, we can't tell if there are any zeros here. So what we should do is throw in some more values. 3.1, that gives us a positive 5.3119, and at 4.5 we get negative 62.13. So it goes from, the y values go from negative to positive to negative. So we know between 3 and 4 there will be a y value of 0. The question just asked for between which integers. So we know that y equals 0 on the interval 3 to 4. And we'll stop there.